Okay, so what if I told you we could take the heat, just the ambient heat in a room, and turn it directly into motion, with pretty much zero waste? I know, it sounds like something straight out of sci-fi, but a brand new research paper is saying, hey, this might actually be possible. So yeah, let's dive right in and see what this is all about.
And get this. This is the claim they make right at the very beginning of the paper. They're talking about efficiencies exceeding 80%. Now, to put that in perspective for you, your typical car engine, well, it's lucky if it hits 20, maybe 35% efficiency. So we're not just talking about a little improvement here. No. This is a potential game changer, a total revolution in how we think about energy.
So what these researchers are proposing is a whole new playbook for converting energy. I mean, forget everything you know about combustion or steam or complex turbines. This is all based on a really deep understanding of physics. We're talking way down at the atomic level. It's a fundamental shift.
And the implications? I mean, they're just staggering. Just think about it for a second. We could have engines that run on nothing more than the warmth in the air around them, or devices powered by simple radio waves. They even talk about a potential new way to control the inertia of a vehicle, which is huge for aerospace. This is the kind of wild future this research is hinting at.
Okay, so the big question, right? How on earth does this actually work? Well, the secret sauce, if you will, lies in three fundamental principles of physics. And it's a good idea to think of these as our toolkit. These are the three tools we need to really grasp what's going on here.
All right, let's open up that physics toolkit. We're going to pull out the three key ideas that make this whole thing possible.
Okay, first tool. It turns out that inside certain materials, some of the atomic nuclei have this little property called spin. And what that spin does is it gives them a tiny magnetic field. Scientists call it a magnetic moment. The easiest way to picture this? Just imagine that every single one of those nuclei is a teeny tiny little compass needle, just spinning away on its axis.
Now, what happens if you take a bunch of these tiny spinning compasses and bring a big magnet nearby? Well, just like a regular compass, they're going to try to line up with that magnetic field. But here's the twist. Because they're already spinning, they don't just snap into place. Instead, they start to wobble or precess around the lines of the magnetic field. It's almost exactly like a spinning top that starts to wobble right before it falls over.
And this is where the magic really starts to happen. You see, if you hit these wobbling nuclei with a pulse of energy, say from a radio wave, at exactly the right frequency, you can literally knock them off kilter. You can force them into a totally different alignment. You're using an external signal to directly control their motion and their energy. And that, my friends, is the heart of what we call nuclear magnetic resonance.
Okay, so we've got a way to control the tiny compasses. But wait a minute, I thought this was about heat. So, where does the heat come in? Well, that brings us to our second tool, something called the magnetocaloric effect. It sounds complicated, but the idea is pretty simple. It just means that certain materials will literally heat up or cool down when you change the magnetic field around them. This is our gateway. This is how we get thermal energy into the system.
And now for the final and maybe the most crucial piece of the puzzle. It's a fundamental law of the universe, the conservation of angular momentum. All that really means is that the total amount of spin in any closed system has to stay constant. It's non-negotiable. So, if you go and mess with the collective spin of all those trillions of tiny nuclei inside an object, well, the universe has to balance the books. The entire object itself has to start spinning to make up for the change. There's no other choice.
All right, so there you have it, our three tools. NMR, the magnetocaloric effect, and conservation of angular momentum. Now let's see how the researchers actually use this toolkit to build something that turns heat into motion. So their first experiment was really just a proof of concept, to see if the basic idea even worked. They took a disc made of a material called bismuth, stuck it in a magnetic field, and then zapped it with a radio pulse. And guess what? It worked! Just like the physics predicted, changing the spin of the nuclei inside made the entire disk physically rotate. They had successfully turned an electromagnetic wave into actual physical motion.
So, building on that initial success, they went on to build this prototype here. You can see the schematic on the left, and then on the right, that's the actual device, the real deal. And this wasn't just about proving the principle again, this was designed to see if it could work as a genuine heat engine.
And the results they got were pretty incredible. Here's what they did. First, they just warmed the device up a little bit. Then, they used a small motor to spin some magnets around it, creating a changing magnetic field. And then, the amazing part. The titanium cylinder in the middle just started to rotate, all on its own. But here's the kicker, the part that proves everything.
As it was spinning, its temperature actually dropped. It got colder, even colder than the room it was in.
Yeah, just let that sink in for a moment. That cooling effect, that is the smoking gun. It's the absolute proof that thermal energy, heat, was being pulled out of the material and converted directly into the energy of motion, kinetic energy. This little device was literally running on the heat from the room.
So you might be asking, why titanium? What's so special about it? Well, this table right here holds the key. You see, most of the titanium out there, its isotopes have a spin of 0, which means they're basically invisible to this whole effect. But a small, crucial portion, about 12%, is made up of titanium-47 and titanium-49, and those guys have a non-zero spin. They are the active ingredients that make this whole thing go.
But it doesn't stop with heat engines, oh no. The research paper actually goes into even more futuristic territory, and this is where it could get really interesting for things like aerospace. So the authors really take this idea and run with it. They actually propose that if you can manipulate the angular momentum of all the nuclei inside an object, you might be able to influence the kinetic energy of the entire object. Now, in theory, this could open the door to completely new ways of accelerating or decelerating a vehicle. I mean, without using rockets or traditional brakes. It's a pretty mind-bending idea.
Okay, let's be clear, this is still very early stage research, but the potential here is just enormous. So it makes you wonder, right? What would a fully developed, mature version of this technology actually look like?
Well, based on the physics, the researchers predicted a device that would be incredibly simple and super reliable. Think about it. No pistons, no turbines, no messy fluids to deal with. It's just a solid piece of material turning heat directly into motion. And because it's not a traditional heat engine, it isn't bound by the same old thermodynamic limits. That means, theoretically, its efficiency could get ridiculously close to 100%. And that leaves us with a pretty profound question, doesn't it? For centuries, we've built our entire world on burning stuff and boiling water to make things move. But what if the key to a truly efficient, totally different future has been hidden this whole time, right there in plain sight, waiting for us to find it, locked away in the fundamental spin of the atom itself?